Hey guys, this is Jan, and today I want to share with you yet another math problem that is disguised as a programming competition problem. The problem was given in one of the educational CodeForces rounds earlier this year, and it actually consists of two subproblems, one slightly easier, another one slightly more complicated, but not terribly so. So the problem is actually a geometry problem. We're given a positive integer n, and we're looking at the regular polygon with 2n vertices, so that its side length is 1. And we're interested in finding a square of minimum size such that you can embed this 2n in the square, so that no corners or any points would go over the area of this square, and we're looking for a minimal of such squares. And as I said, the problem comes in two versions. Simpler one is when n is even. So recall that we're looking at 2n gone, which means that in this case the number of vertices of this polygon is actually divisible by 4. So that's the easier version of the problem, and a bit more complicated one is when n is odd. If you want to give these problems a try, then please feel free to pause this video. I will also put the links to these problems into the description. But to proceed with the solution, I drew a little GeoGebra worksheet. I'm actually a big fan of GeoGebra. It's a wonderful tool to play around with geometry. And so this is what our setup looks like. We have here a regular 2n gon, for instance right now for n equals 4, with side length 1. And this is the minimal square that one can draw around this regular n-gon, such that the sides of the square are parallel to the axis. And to account for all possible embeddings, we can rotate this regular 2n-gon and see what happens to the side length of the square. And it's pretty easy to see that we have the minimal side of the square when some of the sides of this regular 2n-gon for n even are parallel to either x-axis or y-axis. So we see that the now this side length of the square is 2.41. If we rotate it, it first increases up to 2.59, up to 2.661, and then it starts decreasing again until we reach the same position as we started from. It's not a rigorous mathematical proof that this indeed gives you the minimum. I'm simply presenting you some visual aid to help you understanding what's happening in this problem. So we are down to computing this side of the square based on the knowledge that the side length of this regular 2n-gon is equal to 1. And it's actually easy to see what we need to do. We need to draw an isosceles triangle here, where m is the midpoint of this regular 2n-gon. Its base length is 1, and if we are able to find the height of this isosceles triangle, then 2 times this height is going to give us the side of this square. So let's draw this height. So we drop a line from this point M to the side that is perpendicular to this side. So we have this isosceles triangle. Let's also mark the point of intersection here. So we are looking at the right triangle MBS1. We know that BS1 is equal to 1/2. And we are interested in the height of this triangle. So we have two sides sharing this right angle. So it's down to elementary geometry. We know, for instance, that if we have the angle S1MB here, then the tangent of this angle is going to be S1B, which is 1/2, divided by this height that we are after. And what is this angle alpha? In the general case, we see that it's half of 1/8 of full turn, where 8 is right now the number of these vertices, or 2n. So we divide this full turn, which is 2 pi or 360 degrees, by 2n, and then again by 2, so we divide it by 4n. So we can write that. Let's write a nice LaTeX formula. The tangent of this angle alpha is equal to the result of division of 1/2 by this height h. Okay, and where alpha, where alpha is in turn also the result of division of 2 pi by 4n. Okay, so we first compute this alpha. We can do it as we know both pi and n, and then we compute its tangent, and after we have this tangent we can express h as the result of division of 1/2 by tangent of alpha. Okay, and this is basically your algorithm for finding h, and the side length is then going to be 2 times h. So it's actually going to be 1 over tangent of alpha. So this solves the problem for the case where n is even, and I'm not going to write this down in any programming language. You can implement this formula in your own favorite programming language. Instead, let's look at what happens in case where n is odd, and we see that here the situation is somewhat different. So for instance, when n is 5, so we're looking at the decagon. The square size is 3.33 when AB is parallel to the x-axis, but we see that when we move or we rotate this to n-gon, then we still can get a smaller square size, and it in this case goes down to 3.19 something. And and then it starts growing again, and it's important to understand what is this moment that we need to fix in order to start the computations. So it's not when AB is parallel to x-axis. It's rather the moment when this square side will also contain the point F as we turn. this square. And when this happens, it's actually the situation when the points F and D are symmetric with respect to the angular bisector. When drawn from M, if we draw lines through M parallel to x-axis and parallel to perpendicular to x-axis and perpendicular to y-axis, we get a quarter of a plane, and the moment when the square size minimum is when F and D are symmetric with respect to the bisector of this quarter of the plane, this right angle. And this is the key to solving this problem. So basically, we need to find out what is the length of let's put a point here. So we need to find out what is the length of MT1 in this case, and the way you are going to find it out is by using a right triangle MDT1. So one of the key observations is that this length of MD is actually equal to MB, and we can compute it in a very similar way as we computed this H before. And another thing that we are going to need is the size of this angle, T1MD, and we will see in a minute how to find that one. Let's compute this MD, or in other terms MB, first. Let's call this length B, and we can compute it from the very same triangle that we used before. And now we know S1B, and we need this length of the hypotenuse from this right triangle. So we need to divide this length by this length, so S1B divided by MB, and this corresponds to sine of alpha. So we can write that sine of alpha is equal to the result of division of 1/2 by this length B that we're after. Okay, so we know alpha is still the same, so we can compute B from this equation. So we have B, so this MD is also equal to B. And now we need to compute MT1, and we can do it from this triangle, as we said. So it's now MT1, that's length that we are looking for, divided by B is then cosine of beta. So we can write that cosine of beta is equal to the result of division of this length that we're looking at, let it be x, divided by b. Okay. So we know b, and after we get beta, we can express x. So what is beta? So we see that this angle is beta, and actually when we also draw this line and put here the very same also point of intersection, then we see that the angle FMU1 is also beta. So actually 2 beta plus angle DMF Ouch. Okay, I didn't want that. Okay, so plus the angle DMF is 90 degrees. Right? So 90 degrees is this T1 MU1, and beta is half of this 90 degrees minus DMF. So how much is DMF? We see that this DMF itself is a few times this top angle of the isosceles triangle that we already saw. The question is how many times? Right now n is 5, and we need 2 of these isosceles triangles. If we change this 5 to, let's say, 7, then we see that in this case we have 1, 2, 3 of these here. So in general we have n minus 1 divided by 2 isosceles triangles here. So the top angle is n minus 1 divided by 2 times this 1 top angle of the isosceles triangle, which itself is 2 pi divided by 2n. Okay, so let's write this all down. So we have well, okay, let me write it this way, that 2 times beta is equal to 90 degrees minus minus 1 over 2 times this top angle of the isosceles triangle, which is again result of division of the full turn by 2n. Let's see whether this is okay. Yes, so 2 beta is 90 degrees minus n minus 1 over 2 times 2 pi divided by 2n. Okay, this checks out. So n we know, so we can compute 2 beta, we can compute beta. We know b because we expressed it via alpha, which we know. So as a result, we can use this equation to find out x, and the resulting length of the side of the square is 2 times x. So this concludes the problem. I hope you enjoyed it. See you next time.